Okay, so we are going to continue with the forced response. Remember, forced response is also called a step response or complete response. And we are going to mix up parallel and series because we discussed both parallel parallel RLC circuits and series RLC circuits. So some circuits that we are going to do are parallel and some will be series. Approach is the same. Remember that approach is what you have to learn. An approach to solve for either the current in the series circuit or the voltage in the parallel circuit. That approach is going to be the same. Steps are going to be the same. So let's start with our first problem. Okay, let's see. This circuit is determine ILT and VCT for t greater or equal to 0. Okay, yeah. Yes. Mhm.
Is there a difference between 20 volts with step up if you're saying that where T is positive?
Yeah, there's a difference. If it is 20 UT, that means that power supply is going to be 0 before T less than 0, and then after T greater than 0 is going to be 20 volt.
Okay.
In this case, it is 20 volt. The circuit is working until time reaches T is equal to 0, at which the switch is going to open up. So the power supply is going to be out of the circuit. Yeah. So before T is equal to 0, the switch is closed because it is opening up, as you can see, at T is equal to 0. The circuit is closed, the switch is closed, and the current is running in the circuit. And again, our assumption is that it is at a steady state. It's running for a very long time. And initially, of course, before T less than 0, we find our initial conditions as usual. So T less or equal to 0 at T is equal to 0 negative. We're going to find two things: VCT, VC0 negative, and IC0, IL0 negative. So analyze the circuit and tell me what should we use to find the capacitor voltage as well as inductor current at 0 negative. Derivative. Okay. We can definitely, we can do a nodal analysis and we can find the voltage at the junction of R2, R3, and R1. And once we have that voltage, then we can easily find what is the current flowing through R2, which is the current passing through L. And we can also find the voltage across the capacitor. We can also do KVL because the current in the right-hand loop, remember capacitor is open circuit. So you have two loops basically. You have the right-hand loop and the left-hand loop. In the right-hand loop with capacitor being opened, the current is going to be IS in that. So you can apply KVL in the loop which is on the left side, and you can find what is the current in this, and you can easily find now what is the current going through L, which will be the combination of IS and IL. So either way, it's going to be the same. Either we do nodal or we do KVL. It's just going to be one equation, and one equation is going to give you both. I think maybe KVL might be easier because we already know the current there, so it's easier to find the current, or it's directly we can find the current in the left-hand loop, and then we can find the current passing through the inductor as the combination of both IS and the current in the left-hand loop. So I will apply KVL. That might be easier. KCL is easy too, but there's going to be one more step. If you do KCL, then you have to apply Ohm's law to find IL. So I'm going to assign this as loop number 1, and this is my loop number 2. Remember, capacitor is open. L is short, and C is open at steady state. KVL in loop 1. All right, guys, what will be the KVL equation in loop 1? Assume this current to be I1, I1. Yes, say it again. KVL equation. Yes. Yeah. VS1. Yes. Equals I1 R3 plus R2. Say it again. Are you sure? Minus? Plus. IS direction is the same as I1 direction. IS. From that, we can find the value of I1. Okay, let's open Octave. Okay, VS1 equals 20, R3 equals 100, R2 equals 50, L is equal to 200 exponent negative 3, R1 is equal to 50, C equals 1 microfarad, so 1 exponent negative 6, and IS equals 20 milliampere. IS equal 20 exponent. I'm going to make one change here because, no, actually, the change is not required. That's okay. So VS1 is 20, R3 is 100, R2 is 50, L is 200 milli, R1 is 50, C is 1 exponent negative 3, IS is 20, R4 is 70, R4 is 70. Okay. So now my I1 is VS1 minus IS, VS1 minus IS times R2 divided by R3 plus R2. R3 plus R2. 0.1267 or 126.7 milliampere. 126.7. All right. So now we know I1. So what will be IL? IL is I1 plus IS. Yes. One 146.7 milliamps. All right. So this is my initial value of the inductor current. Okay. Now look at the circuit and tell me how are we going to find out the initial value of the capacitor voltage. So how are you going to find that? Yes. Anyone? Mike, how are we going to find it? VC. We have everything to find VC, by the way. Say it again. R1 to V. Okay, so give me the equation. How are you going to find the capacitor voltage? What will be the equation of that? IS times R1 No, that's the voltage across R1. Okay, you have to say it again. I didn't hear you. What did you say? R1 IS, that's IS. Okay, you have to tell me again. I don't think I'm following you. You said IS times. What is I2? I don't see any I2 on the circuit. Yes, there is. IS times R1 and plus R4. But that's yeah, but that's going to be the voltage across that series combination R1 plus R4. That would be across that. That's not the voltage across capacitor. IL times R2 plus IS times R1. Excellent. Very good. Okay, so observe, guys. You go this route because you have to find the voltage at this point, right? So you take this route, you know the voltage passing here, you know the voltage passing here. So you start, assume this is ground, of course, start here, IL times R2, and then IS times R1. That's going to be the voltage at this moment, right here. 8.33 volt. Yes, yes. IL is passing through that. L, of course, L is short, so there's no voltage drop in L, but there's going to be voltage drop in R2, and then there's going to be voltage drop in R1. And when you add those two voltages, you're going to get the voltage at the top of the capacitor. Yes.
I only want to know why R4.
Why should I take it into account? Answer that first.
So this is how I'm interpreting this as well, as the voltage that goes pointing from ground, going up, and going to the right.
Okay.
So we know the voltage across IL right there, which is
Mhm.
with the current though, isn't there voltage that's pushing that current up through IL and going through R4 and going to the left?
Did you get to the node at which you are trying to find the voltage though? You get to the node already? Why do you want to move beyond that node, right? Okay, so we find now the two initial conditions, and now we're gonna solve the circuit for t greater than 0. So for t greater than 0, of course, switch is going to open up. That means R3 is gone, and we are left with this circuit. Let's redraw the circuit. R2L. R1 capacitor. And R4 So this is a circuit that is left after t greater than 0. What do we do first thing when we are analyzing RLC circuits for forced response? Fine. Good. Okay, now what type of circuit do we have? Parallel or series? Natural circuit, that is. We have a series circuit, natural, because of course for natural circuit you have to remove the current source, and when you eliminate the current source, it's going to become open. So R4 is going to be gone. That means you will be left with a series circuit. So it's a natural circuit is the series RLC circuit. And since we have a forcing function, IS, therefore the total response is going to be the sum of steady state response and of course natural response. So ILT will be equal to IL steady state plus IL natural, and similarly VCT will be equal to VC steady state plus VC natural. So remember, when you are analyzing the circuit for either series or parallel, you have to look at the natural circuit. So remove the sources and then look at the circle to decide if it is series or parallel. In this case, when you remove the source, of course, it's going to become a series circuit. So let's go ahead and find the damping of the circuit. Let's see. Let's open series RLC translate. Okay. So in this case, R1 plus R2 is going to be the equivalent series resistance, and then L, and then C. So A is alpha is 250 radian per second, and omega naught is more than alpha, therefore it's an underdamped circuit. Check if you're getting the same result. No, why R4 in series when you remove? Say it again. Yeah. Source is gone, R4 is gone. No, but for the damping type, you have to analyze the natural circuit. So you have to remove sources when you're analyzing the damping type, either parallel or series, you have to remove the source. For damping type, you remove the source. So voltage source is going to be short circuit, and then current source is going to be open circuit when you're looking at the natural circuit. You getting the same result? Then write it down. How long is it going to take? 2 minutes to write the code. You need to have those programs with you guys, or you're going to take forever to do it with the calculator. Anyone can confirm my values? You got it, Mike? You got it? Okay, good. And if you guys, after telling you guys over and over again, still if you don't have the code, still you're not following, don't blame me when you are going to take forever to finish it in exam, and then some questions will be left and all those things. Okay, so That means our ILT expression is going to be the steady state response plus e to the power negative alpha t a1 cosine omega dt plus a2 sine omega dt. Since it's an underdamped response, this will be the shape of the response for the natural circuit. Okay, who is going to tell me now what will be the steady state value of the inductor current? You don't tell me right now. Somebody else is going to tell me, and tell me quickly. What will be the steady state value of the inductor current? Say it again. No, steady state value. Steady state. Yes. Yes, very good. Why? Capacitor is open, exactly. Capacitor is open, inductor is short, all the current is going through R4, R1, R2, and inductor since capacitor is open. So steady state value of the inductor current is Is. All right, how do we find A1 and A2? Who is going to tell me that now? Yes. First, we're going to use initial condition. At t is equal to 0 negative, IL0 negative is equal to Is. This is going to be 1, and then this is going to be 0, so A1 is going to be left. 0.1267. Okay. And are we going to find A2? Take the derivative and then do what? Evaluate the derivative at 0 negative. Okay, Is of course is constant value. Derivative of that is going to be 0. So this is going to be left. Anybody remember what did we discuss? What is the derivative of this? At t is equal to 0. Okay. No, A1t plus A2. All right, so negative alpha e to the power negative alpha t, and then this is going to be the same. So when you put t is equal to 0, it's going to be negative alpha times A1. So negative alpha times A1 at t is equal to 0. And then derivative of this will be omega d A1 sine omega dt plus omega d A2 cosine omega dt. Again, at t is equal to 0. This term is cosine is going to be 1. So it's going to give you A2 times omega d. Omega d times. And since we have done it over and over and again, therefore I don't want to waste my time. Do it. I just did it verbally, and then I wrote down the equation based on. I don't remember the equation, but I can do it verbally and then put down t is equal to 0 to do it. Now, as I mentioned last week, make sure you take the derivative, and then you put t is equal to 0 to show that this is going to be the result. Don't just memorize this. I don't memorize this equation. So negative alpha A1 plus omega d A2 at t is equal to 0. When I plug in t is equal to 0, then I'm going to get this result. 0 positive, basically. 0 positive. Okay. How do we write di over dt? Yes, di over dt is dil over dt. VL over L, very good. VL0 positive over L. You guys know that Wednesday is your quiz, right? And the way nobody is answering, I don't think the quiz is going to be very good. Okay, now let's look at the circuit and decide how we're going to write down VL. This is VL. How should we write VL in this circuit? Okay, use KVL in the left loop, I'm assuming you're saying, right? Okay, so what will be the equation? What will be the equation of KVL in this loop? Okay, so negative VC plus IL 0 positive R1 plus R2 plus VL is equal to 0, right? So VC is equal to VC, and we are evaluating at 0 positive, so I'm going to put 0 positive. VC 0 positive equals IL 0 positive R1 plus R2 plus VL 0. Okay, observe this equation and tell me if this equation is correct. KVL equation. Of course, IL 0 positive will be flowing through since R1 and R2 are in series, going through R1 and R2. Make sense? Right? Now we know IL 0 positive, we know VC 0 positive, so we can find VL 0 positive from that equation, VC 0 positive minus IL 0 positive R1 plus R2. And that's what circuit analysis is, right? Remember, guys, you look at the circuit and you analyze it. Equations, solution is not difficult. Analysis is what is important. And that's what I've been trying to teach you since the beginning of this semester as analysis. Of course, look at the solution. We're doing solution, again, using MATLAB or something. Solution is not difficult once you analyze the circuit correctly. So VC 0 positive minus and since we are analyzing A2, oh, I'm still using grape, man. Anyways, since I'm using it, I'm just write this equation down. So that's going to be plus alpha A1 and then divided by omega D, and that's 8. Let's calculate that. A2 is VC 0, VC 0 minus IL 0 times R1 plus R2 divided by L plus alpha times A1, everything divided by omega t. And I'm getting a 0. Anyone else who's getting a 0? Got a 0? Okay. So which implies now that ILT is the steady state value, ILSS, that we found out to be equal to IS, and IS is 20 milliampere, and A1 e to the power negative alpha t, and A1 is 126.7 milliamp. So plus e to the power negative alpha is 250. 250 t A1. A1 is 0.1267, so 126.7 e to the power negative 250 t cosine omega d is 2222. No, yeah, 2222. And the whole thing is in milliampere. This t greater. That will be the expression for IR. If you have any question, please go ahead and ask. Again, at t is equal to 0, this will be 1, this will be 1. So initial current value will be 146.7 milliampere. And just make sure to check that that is the value that you have. Initial value of inductor current is 146.7 milliampere. And final value is 20 milliampere. So 146 milliampere initial value, and final value when the second term is going to die down because of the exponential function, you will be left with the steady state value of the inductor current, which will be the source value, 20 milliamp. Okay, he was going to tell me how we're going to find the equation for the capacitor voltage now from this circuit. Yes. Say it again. It's right there. That is correct. It's right there. Here we are. VCT is equal to ILT R1 plus R2 plus VLT. KVL that we applied in that loop, that gives us the capacitor voltage. All right, VLT, How are we going to write VLT? LDI over dt plus. All right, IL is this, of course. So L times derivative of this. Derivative of 20 is 0, of course, and then derivative of that term. So this was 126.7 was A, I'm assuming. I'm just going to write down variables. So A1 and the derivative of this e to the power negative e to the power alpha t, right? Negative alpha t. So e to the power negative alpha t. Actually, I'm going to pull A1 out. L times A1 e to the power negative alpha t, and then derivative of this, which will be negative 2, 2, 2, 2 sine of 2, 2. And then the derivative of the first term, which will be negative. Why I'm putting 2, 2, 2, 2. I'll put alpha omega d. Since I'm putting everything in terms of variable, I'm going to put this in terms of variable as well. So negative omega d sine omega dt. And then the derivative of the exponential term, which will be negative alpha e to the power negative alpha t cosine omega d. So that's the derivative of the current, and then R1 plus R2 times the current. R1 plus R2 times current, which will be, the first term is IS plus A1 e to the power negative alpha t cosine omega d. And now I'm going to combine the like terms and then just solve, simplified, or solve for the values. So my like term, of course, I have a constant value, which is R1 plus R2 times IS, R1 plus R2 times IS. That's my steady state response of the capacitor voltage. And then my transient response is comprised of course, the underdamped response, which is cosine and sine. So I'm going to write down cosine terms together, plus R1 plus R2 times A1, or I can write down e to the power negative alpha t first, since it is common in each term. So e to the power negative alpha t, and then R1 plus R2 times A1, and then from the first term, negative, right here, negative alpha times L times A1. Negative alpha times L times A1. This is for cosine term. So I'm going to put another parenthesis, cosine omega dt. And then for sine, I have just this term for sine, negative omega d L A1 E negative, E already there outside. Sine omega d these are everything in terms of variable, and again, make sure you do it. So if I make a mistake, then you tell me that I'm making a mistake. So R1 plus R2 times IS, and there's my VC steady state. It's not coming out to be correct value. It's coming out with 2 volt. I thought it was different than 2 volt. Or is it 2 volt? Oh, we did not find a steady state. Let's see. Is that going to be 2 volt? R2 plus R1. What is R2 and R1 values? R1 is 5 and R2 is 5. So 100 times IS, which is 20 milliampere. Yeah, so that's going to be 2 volt. That's correct. So steady state value of capacitor voltage will be 2 volt. Two. R1 plus R2 times A1. R1 plus R2 times A1 minus alpha times L times A1. That's 6.33. 6.33 cosine 22T and then minus omega D LA. Omega D times L times A1. 56.29. 56.29 sine 2222 volt for t greater or equal to 0. Does this equation look correct to you? How are you going to check that this equation is correct? Well, or at least you say, okay, well, because of this, this equation may be correct. How are you going to check that? You're going to check for the initial condition and you're going to check for the steady state value. So steady state value is 2. And again, you can check from the circuit. If a steady state value is 2, as we just discussed, it will be 2. And the initial value of the capacitor voltage at t is equal to 0 is going to be 2 plus 6.33, because that sign is going to be 0. This will be 1, this will be 1. So the initial value is 8.33. And just go and check if that's the initial value that we calculated, 8.33, which is right here, 8.33 volt. So at least from these two values, steady state value and the initial value, I can say that equation seems correct to me. Sure. Well, I did it in front of you, right? Yeah. What alpha equation you're using? R over 2L? Okay. Well, R over 2L is gonna come out to be 250, I'm pretty sure. Let me check. So R, remember R1 and R2 is R1 plus R2, right? So R1 plus R2 divided by 2 times L. Let me move this here so you can see. There you go. So it is coming out to be 250. At the bottom, you can see that. Let me make it bigger so everyone can see. Okay. Natural circuit, of course, is without the current source. So when you remove the current source, it's going to become open. Okay, guys, this turned out to be a good problem. I just created that, but turned out to be semi-complicated problem, I would say. But again, as long as your concepts are clear, irrespective of how the problem is given to you, you should be able to solve them. But that's the problem. The concepts, you guys don't have good concepts. That's the biggest issue. And you guys know that. All right, any question that you may have from this problem? Again, make sure keep learning, keep learning, and eventually you're gonna learn, hopefully.
Find the data points, right? We want to go ahead and find out our steady state, our natural.
Yeah, once you find damping of the circuit, then you write the complete response in terms of the steady state response plus natural response, right? The steady state response is when time hits infinity. So basically, capacitor is open, inductor is short. Using that condition, you find the value of the inductor current, a steady state response for series circuit, or capacitor voltage for a steady state response. And then the natural response will, the shape of the natural response depends upon the damping type. So in this case, since it's an underdamped circuit, we wrote down the shape of the response is going to be an exponentially decaying sinusoidal response. And from that, you will have to find out the two unknown values, A1 and A2. Now, one value is always easy to find because you're putting initial conditions. The other value may be harder to find when you're taking the derivative of the current in this case, because then you have to go back to the circuit and then you have to analyze as what will be the equation that you're going to put in terms of the inductor voltage, if it is a series RLC circuit, and if it's a capacitor, then the capacitor current. Because capacitor current appears that when you take the derivative of the voltage, capacitor voltage, and inductor voltage appears when you take derivative of the inductor current. So from the circuit, you have to write down that equation in terms of the initial values. And that is, I believe, that is where, that is the challenging part. Basically, that's where you have to pay really good attention as how you're going to write that equation in terms of VL 0 positive for series RLC circuit and IC 0 positive for parallel RLC circuit. That's the challenging part, I think. Especially when you have sources in the circuit, when you have the forced response. If you don't have forced response, if it's just a natural circuit, then it's pretty straightforward because you just have a natural circuit series. So voltage across the inductor is going to be sum of the other two voltages. And then for the current going through the capacitor in the parallel RLC is going to be the the sum of the other two currents or subtraction of the other two currents, IL and IR. But when you have the source, in this case you have one source, let's say if you have two sources or three sources, and if you remove those sources, your circuit is still parallel or series. So it's either series damping or parallel. But if you do have sources, then you have to really analyze the circuit to see how you're going to write down VL 0 positive and IC 0 positive. That's challenging. Yeah.
So do you think it's disadvantage to, for example, under this circuit, like that. So for the mistake that I made when I went back and calculated alpha, I had included R4, but you think there's a disadvantage, so you just drawing it where there is no source in R4 up there.
Well, R4 is not there if there's no source anyway, right? So I don't know.
Just by drawing it.
Just visually, just look at visually. Why you have to draw it? I mean, if IS is not there, IS is open circuit, of course R4 is not there. R4 is hanging in the air. So your series circuit does not include R4. You can see that. Those are, I mean,
I know those are like little things that you got.
Yeah, that should not happen. That's what I'm saying. Yeah. Okay, guys. Any other question that you guys may have from this? And again, as you can see, I use everything I use in terms of variables instead of putting numbers, because just as you saw that, just make calculations easy because I have values assigned to all these, and then I can just go and write down the equation and MATLAB can calculate everything for me. Instead of putting the numbers and all those things, it's just waste of time, and there are more chances of making mistakes when you're putting numbers. Okay, let's go ahead and work on one more problem then before we take a break. Let's see. All right, let's do this. I'm going to put the time later based upon the damping and time constant. And I'm going to put the time again over here later when we calculate the value of Nepper frequency. So we're going to find three things, or four things basically. We're going to find the expressions for ILT and VCT, and then we're going to find energy stored in the capacitor at a time that I will put down a little later, and then power dissipated in R1 again at a time, then I'm going to put down a little later. Before we start solving the circuit, actually, of course, IL and VC we are solving over and over again in last few problems. Who is going to tell me the second part? How are we going to find out the energy stored in the capacitor at some time t is equal to, which will be greater than 0, of course. I'm going to put down that time, but how are you going to find that energy stored in the capacitor? Who is going to tell me that? Okay, and what is the formula? Half CV square, right? So when I put the time, let's say I put 10 millisecond, how are you going to find that energy at 10 millisecond? In the voltage expression that we will find in the first part, you're going to put 10 millisecond, find the voltage at that value, at that time instant, and then use that. Very good. What about the power dissipated in R1? How are you going to find the power dissipated in R1? Again, let's say time 10 millisecond. How are you going to do that? Say it again. I square times R1, and we're going to use I at in the current ILT, because it's the same current that will be passing through R1. Very good. So again, have your mind very clear as how you're going to find it, instead of be doubtful about if you have IL, VC, how you're going to find the other two. Those two are related directly to the expressions for IL and the expression for VC. The second and third part are directly related to those two expressions. So basically our job is to find IL expression and VC expression, and then second and third will be very easy. So what is the first thing that we do when we are solving the circuit? Again, observe circuit. There's a switch that is going to open up at t is equal to 0, leaving the right part of the circuit to be open, hence eliminated from the circuit, which will leave us with what type of RLC circuit? Yes, series. Yeah, series. Okay, what is the first thing that we do when we are solving for the current and voltage across a capacitor? We find initial conditions. So at t is equal to 0 negative, IL0 negative. Okay, who is going to tell me how are we going to find IL0 negative? I know you know, so don't worry about it. Anyone else? Did you say something, Florian? Okay, apply it and tell me how you're going to find it. I won't go to KVL, but if you're saying KVL, you can also use KVL. I won't go to KVL. It's not that difficult. So, okay, so you always use variables. Don't tell me 10 or something. Use variables, which, okay, VS1 plus VS2, okay. No. All right, anyone else? Okay. So again, say it again, VS1. Uh-huh. Yeah. No, not VS1 plus IL times R1. Good. Okay, VS1 equals to what? Okay, keep going. No, incorrect. Yes, yes. Go ahead. Natasha. Okay. Multiply with what?
Oh, sorry. No. Yeah. So
VS1 minus VS2 equals 0? No. All right. Yes, Chris. Uh-huh. Right. So that's the equation. That's the KVL equation, which is good. But I'm going to apply Ohm's law. I mean, L is short circuit, capacitor is open circuit, so that branch is gone. L is short circuit. So you have a single loop with two resistors R1 and R3, and the voltage on the left side is VS1, voltage on the right side is VS2. So it's VS1 minus VS2 divided by R1 plus R3. That's your current. So instead of going KVL, the KVL is going to give you the same equation. It's not incorrect. I'm not saying it's incorrect. KVL is going to give you the same equation that you told Chris. That's the equation for KVL. That's a correct equation, and you can get the current using that equation. But start easy. Don't jump to KVL, KCL if it's Ohm's law. VS1 minus VS2 over R1 plus. All right. So Chris, again, what you said is a correct equation though. And from that equation, you're gonna get the same equation for IL. Yes. I'm sorry? From what? Oh, we did that, and still you guys cannot tell what's that's not good, man. That's not. It's not the same question. Okay, so all right. we did that and it's still nobody could answer it. So which is yeah, I don't have to say anything else. That means you guys are not reviewing lectures at all. Once again, guys, the best practice that you can do is to resolve these problems without looking at them. And if you're not doing that, you're not getting practice. $2.27 milliampere. All right, guys. Since we already did this problem, everyone should know how to find VC0 positive. Who's going to tell me that? Yes. Reyes.
Yes, sir.
Times R1. Yeah. VS1 minus ILR1. Okay. So I'm just going to do this. And since we already did that, no need to go through that. Just write down the equation and do part number 2 and part number 3 then. I didn't know we did that. And again, that does show you that you're not in a good shape. Okay, let me open the notes then. What was the 26th, right? Yeah, we did that. That's right here. 7.27. 27. Okay, so I'm not gonna do this. So let's write down so this problem. This problem was done last week. So let me write down, it's a critically damped circuit. And let me write down the equation of ILT. E to the power negative 10,000 T. 4.54 T plus 2.27 exponent negative 3 ampere T greater or equal to 0. And then I ask you to calculate the capacitor voltage. And that is Vs minus L di over dt, IL, dIL over dt, minus IL R1 plus R2. And I ask you to solve this. Anybody got the expression? I ask you to finish this problem. Anyone got who finished this problem and got the expression? Anyone? Some people said that they finish it. Who finished it? Lazaro, did you finish it? Okay, give me the expression then if you finished it. And if you did not finish it, hey, when you see your exam result or quiz result, blame just yourself. Don't blame me. That's VS1. VS. Forced response. The one, I think we did one problem. I think this is the problem that we did for the forced response. All right, V+1 is 10 minus A1 e to the power. A1 times L. Four, 5, 4, 0. Okay, what do we have? Negative O times negative alpha A2. Negative O times negative alpha times A2. Negative L times A1. Negative L times A1. Okay. And negative R1 plus R2 times A2. Okay. Negative 2 point. .72. This is what I'm getting. Could be wrong, most likely correct, but I don't want to spend a lot of time. This is what I'm getting. If you would have finished it, then of course we could have compared the answers. I don't want to spend a lot of time solving things, but this time is important. So this is the voltage expression that I'm getting. Alpha, of course, is 10,000. So now we go back and let's see our time constant in this case is 0.1 milli. So let's go back and put this as 0.05 millisecond, 0.05 second. So we're going to find the energy stored in the capacitor at 0.05 millisecond, and the same at the same time, what is the power dissipated in R? And we have the formula half CV squared, so CVC 0.05 milli squared. So WC is equal to C times, let me just calculate VC first. VC is n minus exponent of negative A times T times 2.724, 2. Okay, so VC is 8.334, and that is going to give us WC is C times VC by 2. So I'm getting 3.47 microjoules for this. 3.47 microjoule. Yes. Uh-huh. I put, I'm sorry. I put what? Uh-huh. You're getting what? 3 point? For what? For energy, you're getting 3.37 what? Micro or just 3.37? Microjoule? Okay, so you're using the same expression? Oh, I'm missing a 40 over there. Oh, yeah, I'm missing. I say 4740, right? 4540. Right? I'm putting 454. Okay, so I'm missing a 0 over there. Let me go back and do it. 4540. And then 3.37. Yeah, you're right. 3.37. 3.37 microjoule. And then power dissipated in R1. equation for IL is exponent of negative alpha times t times a1 times t plus 8. Okay, so PR1 is IL squared times R1, and this is 2.75 milliwatt. Okay, so let's do the problem maybe. Okay, so we have to find both the capacitor voltage and inductor current after t is equal to 0. All right, guys. So what is going on before t is equal to 0? Yes. Before t is equal to 0, how you can analyze the circuit? Yes. Very good. So it will have both sources active before t is equal to 0. And before t is equal to 0, of course, we have to first find the initial conditions of VC and IL. So who is going to tell me how we are going to find VC and how we are going to find IL initial conditions in this circuit? Or what is going to be VC 0 negative? Who's going to tell me that without even doing any calculation? Yes. Yes. You're saying something? Okay. So say it again. What did you say? IS? IS times R2? Okay, IS times R2. That's one answer. Is that answer correct or incorrect? Is that VC0 negative going to be IS times R2? Hold on. Yes, Mike. What is VC0 negative in this circuit? Oh, that's what Chris said. Voltage across capacitor is going to be what? I'm sorry. I don't know. What do you mean node sharing? Yes.
Because if they do IS2 R2 and the result of voltage R3.
Yes, Gloria. So what is the voltage? 0. Voltage is 0, guys. Come on, guys. Come on. Inductor is shorted. It's t is less than 0. Circuit is running. Inductor is shorted. Capacitor is open. No initial voltage across the capacitor because it's a parallel RLC. Well, LC and R2 are in parallel to each other. And of course, when inductor is short, since at a steady state it's going to become short, capacitor voltage is going to be 0. Okay, how are we going to find the inductor current now? Vs divided by R3. I don't think so. Anyone else? Well, yeah, it's not Vs divided by R3. It could be part of that, maybe Vs over R3, but not. What will be the inductor current? Say it again. Okay, you are very close, but why minus? Are the current direction opposite? Okay. Yeah, but it's going up, and then how is going to flow through L? So it's going to be the combination of two current. It's going to be VS1 over R3, what Gloria you said, VS1 over R3 in that loop on the right, on the left hand side. And then IS is also going over there. It's not going to pass through R2. It's not going to pass through C. It's going to go through L because L is shorted out. So it's going to be the combination of IS2 plus the current that is being supplied by VS1, which will be VS1 over R3. So if we call this I1, I1 is VS1 over R3 because this is shorted out. I'm sorry? IS2, yes, IS2. .501 or 501 milliampere. Okay, when time exceeds 0, what's going to happen to the circuit? IS2 is out. So redraw the circuit, R2, C, L, R3, VS1. Okay. So let's start, let's actually discuss what type of RLC circuit do we have, natural RLC circuit do we have, parallel or series? Parallel, okay. So if you want to find damping type, what, what resistance do we have as far as natural RLC circuit is concerned? Say it again. Parallel combination of R3 and R2. Remember, VS1 is going to be shorted out if you look at the natural circuit. So R3 and R2 are going to be in parallel with each other, and their equivalent resistance is going to be parallel of R3 and R2. So we're going to find out damping type. So let's go ahead and do that. Yes, go ahead. Yeah, the thing is, I'm not doing it because you guys are struggling like crazy. So I have done those problems last time when I taught the class with two capacitors. Method is the same. Of course, you have to do a little more analysis of the circuit, but purposefully, I'm not going into those because even with these type of circuit, only you are the one who's giving me the answers, and everyone else is just. So if I start doing those, I think it's just going to be a waste of time, to be very honest. But yes, the method is going to be the same, but analysis is going to be a little deeper as how you're going to find the charge on the current passing through one inductor and the current passing through two inductor. At the end, first, of course, you can combine inductors together, capacitors together, make parallel or series RLC circuit, and then you have to expand them again to see how to find individual voltages across capacitor, individual current, if it is parallel RLC circuit, individual currents across the inductor. So analysis becomes a little more involved. So with what's going on with this class, I don't think it even makes sense for me to do those problems, to be very honest. So that's why I'm just limiting myself to one capacitor and one inductor. Okay, so now let's go ahead and find the damping type, and this is the parallel circuit. All right, seems like it is an overdamped circuit. Let me know if you get the overdamped. These are the values that I'm getting. Ten, 50, 20, 10. Anyone else getting the same result? Okay. Okay. So if I go with finding the capacitor voltage, it's going to be the steady state value plus the natural response. Steady state value plus A1 e to the power S1t plus A2 e to the power S2t. Okay. From the circuit, what is the steady state value of the capacitor? Yes. Why capacitor is removed? No. If it is running for a long time, that's t is at a steady state. But when t greater or equal to 0, we are trying to find the equation that it starts at 0 and then it goes for all values of the t. When you are evaluating steady state value, then you assume it's running for a long time. That's one part of the equation. VC is steady state plus VC natural, but when you assume natural response, then you don't assume it's running for a long time. That's what we've been doing for the last like 5 problems. To find the steady state response of the capacitor voltage, then you assume it's running for a long time. That's what we are trying to find first. VC steady state plus VC natural. For VC natural, of course, since it's an overdamped circuit, this will be the response type. Because for the natural response, as I've been repeating over and over again, you remove sources and you see how the circuit looks like. When you remove the source, what's going to happen? Or they will be in series. Are they connect? Are the same? Is the same current flowing through R3 and R2? If you remove VS1, then R3 and R2, how they will be connected? If you remove, like removing VS1 is what? Means what? What you're going to do with VS1? Short circuit, right? So if you short circuit that, look at R3 and R2, how they will be connected if you short that source. No, don't worry about inductor. I said remove the source, right? When you remove the source, you said you replace it by a short circuit, short wire. Okay, if you replace it by a short wire, then R3 is connected between these two nodes, and R2 is connected, and L is connected, and C is connected. All four components will be connected between the same two nodes. Okay, so we were discussing the steady state value of the capacitor voltage. Who is going to tell me what will be the steady state value of the capacitor voltage? Chris, you know that. I'm sorry? Voltage across what? The steady state value of the capacitor voltage is not voltage across R2. I don't know how I don't even have words now. Steady state value means capacitor is open, inductor is short. Inductor short means capacitor voltage is going to be 0. We just did that like in this problem, and the same problem we did. Okay, guys, how are we going to find A1 and A2? Who's going to tell me? Okay. T is equal to 0 negative or 0 positive. A1 plus 8. And we see 0 positive is 0 because we see 0 negative is 0. So A1 plus A2 is equal to 0, which is our equation number 1. And now we're going to take the derivative of this. And that will give us A1 S1 e to the power S1t plus A2 S2 e to the power S2t, which at 0 is going to give us A1 S1 plus A2 S2. Okay, so derivative of the capacitor at with respect to time. If you go back to the circuit. By the way, first, how are we going to replace this equation? With what? IC over C. All right, now go back to the circuit because you have to write down, and this is what I'm saying. This is challenging a little bit. Perhaps this is the only challenging thing. So we are looking for this IC, and then of course we have different currents. We have this current coming. Let's call this I1, IL, IC, and then of course you have IR2. So how we can write down IC from the circuit? Yes. IC is equal to what? Okay. No, that's not IC. You're mixing signs. Your equation is correct, but you're mixing signs. Look at the direction of currents again. I1 is going in and it's dividing into those three currents. So IC will be equal to what? Yes, Rudley.
IR2 minus
No. Yeah, go ahead. Say it again. Yes, I1 minus IR2 minus IL. KCL, I1 is dividing into these three currents. So IC will be equal to I1 minus this current minus this current. I1, and I'm going to write down 0 positive, minus IL 0 positive, minus IR2 0 positive over C A1 S1 plus A2. Okay, IL 0 positive we know. How are we going to write down IR2 0 positive and I1 0 positive? Let's go back to the circuit. Okay, IR2 0 positive. Who's going to tell me what equation I'm going to use for IR2 0 positive such that I can find IR2? And then of course the same thing with what equation I'm going to use for I1 0 positive such that I can find that value. Not difficult, very easy. Yes. No, look at the circuit. I don't have to scroll down. You're giving the answer from the circuit. I'm asking you what is the equation for, we already know IL 0 positive, right? From the initial condition that we know. We don't know IR2 0 positive. We don't know I1 0 positive. So how we can write IR2 0 positive and I1 0 positive such that we can find those values? Yes, they're in the circuit right there. Everything is in the circuit. VS1 is what? VS1 is not across R2. What are you talking about? Yes. Mike, Rodley's, Reyes, Natasha, Lazaro, anyone. Gloriana. Yes, Gloriana. Times? Okay, that's IR2. Very good. What about I1? I1. IL we know already. IL 0 positive we know already. Mike, what's going to be I1? No, just I1. Give me the equation for I1. Don't worry about anything else. I1. What is the equation for I1? Yes? No? Yes, Taylor? Okay, well, I'll explain it. Yes, Natasha? No, I1 is not the voltage. I1 is the current. It's split into three currents. As you can see, it's split into IL, IC, and IR2. Three currents. I'm asking you what's the equation for I1 that I can write such that I can find the value for I1 at 0 positive. All right, now Yunus is going to explain. Yunus. No, there is no short right now at 0 positive. At 0 positive. You can have short, but I'm just asking you, give me the equation, just the equation. We can discuss later what is short and what is not short. Just give me the equation. Okay, that could be very well be, right? But what if I want to write down the equation at any time? Let's say not zero positive, at any time. What equation is that going to be at any time? If I want to write down I1 equation at time t, what will be that equation? VR3 over R3 is I1, but again, we don't know what VR3 is. What we know based on that. Yes. No. I'm just asking I1. All right. First lecture, Ohm's law. How do you apply Ohm's law? No. Ohm's law. What voltage do you take across the resistor? You take potential difference. You take potential difference, voltage on one side minus voltage on the other side.
So VS1
Vs minus Vc over R3. At any time, Vs minus V3 or Vc over RT, irrespective of what is zero. For zero, of course, Vc is zero. R3, the other side is the capacitor voltage, Vc. The other side is Vs1. I1 is Vs1 minus Vc over R3, first lecture. Or go back to IET, go back to DC circuit, go back to AC circuits. I mean, come on, guys. All right, negative 0.5. Vs1 minus Vc0 over R3 minus IL0. Divided by C. See if you're getting the same result. Is everyone getting the same result, different result? Let me know. Same thing? Good. Okay, now we're going to solve simultaneously equation number 1 and equation number 2. And let's see, first equation is 1, comma 1. Oh, by the way, Taylor, did you get your answer? Did you get the answer? Okay. Okay. So I got A1 negative 0.7408 and A2 is positive 0.7408. Okay, good. So my VCT is 0.0174. I'm going to write down S2 first because S2 is positive. So S2 is negative 31.861 e to the power negative 31. You can, it's just going to be negative. That's why, right? S1 is negative. The coefficient for S1 is negative. So I'm putting it second. All right, the second thing is, or the last thing is to find the inductor current. So now go back to the circuit. Who is going to tell me how we're going to find the inductor current? I'm sorry? Say it again?
So
Okay. And so what we're going to write down?
So
Okay, sorry. Say it again one more time. Negative IR2, okay. Minus IC. Okay, so I1 minus IC minus R2. Yeah. That's IR or IR2. What is that? What designation did I? IR2, right? Okay. All right. So who is going to tell me how I'm going to calculate I1T? Okay, and that is going to be VS1 minus VCT over R. Okay, what about ICT? How are we going to calculate IC? C dVC over dt. Very good. C dVC over dt. And what about IR? How are we going to calculate IR2? You don't have circuit with you? IR2. VC over R2. All right, so we have the equation for VC right here. So it's very easy to evaluate this equation. I'm not going to do that because it's going to take me some time. So I'm going to write this down, which I assume nobody's going to do it, but at least I'm just going to write it down to finish it. All right, and this concludes parallel RLC circuits, chapter number 9 in the book. So on Wednesday, we are going to start sinusoidal response, steady state sinusoidal response. So steady state sinusoidal response is basically, remember, anytime you have, again, inductors and capacitor, they will charge and there will be a transient time that they are charging and discharging, right? But when we discuss steady state sinusoidal response, we are ignoring the transient and only solving for the steady state value of the sinusoidal response. That is, a steady state value of sinusoidal response is still going to be sinusoidal response because the steady state value matches what type of source do you have. If you have a DC source, your steady state value is a DC value. If you have a sinusoidal source, your steady state value is a sinusoidal value. If you have a square wave, your steady state is a square wave. Now, everything will have transients because as long as you have capacitor and inductor, you do have transients. But when we are discussing a steady state, we ignore transients and only concentrate on what's going to happen when all the transients are died out and you have a steady state response. So that's what the topic for chapter 10 and the following chapters basically. Let me stop recording and then we can discuss it.